In this video, we are going to learn how to evaluate surface integrals of scalar functions. So let S be a smooth surface defined parametrically as r of u v on the domain D, and f of xy be a continuous function defined on S. Then the surface integral of the function f of xyz over the surface S is given by the double integral over S of f of xyz ds, so there's our surface integral, and we'll evaluate this by defining everything in terms of u and v. So this is going to be the double integral over the domain D. We'll redefine the function in terms of u and v with our parameterization, so f of r of u v. And then if we remember from our work with surface area, the ds is going to become the magnitude of the partial of r with respect to u crossed with the partial of r with respect to v dA. And that's how we're going to evaluate a surface integral of a scalar function. All right, so that whole piece here is the surface area element that we're integrating over. That ds tells us we have a surface integral. The function that we're integrating, that's the scalar function. So the process here is very similar to evaluating a line integral of a scalar function, where we redefine the function in terms of t with our parameterization, and then the ds, which was a lowercase s in that integration, was the magnitude of r prime of t dt. And now we have the magnitude of a cross product, dA, since we're working over a surface, not a curve. If the surface is defined explicitly as z equals g of xy, then we can express the integral as. So essentially here, if we were to use a trivial parameterization, we can make the process a little bit more efficient for evaluating. So we're going to get the double integral over the domain D still. Now we're going to redefine the function. So it's going to be xy, g of xy. So there's our trivial parameterization there. And then instead of the magnitude of the cross product, we're going to replace that part of the integral with the square root of 1 plus the partial of g with respect to x squared plus the partial with respect to y squared, and then dA. So this now, whole term, replaces the ds. And we saw this when we were computing surface area and the surface was defined explicitly. We often went this route by setting up the square root of 1 plus partial with respect to x squared plus partial with respect to y squared. It saved us the process of doing a cross product and finding a magnitude, so it was a bit more direct. So we'll use both of these definitions throughout the video based on the surface that we're integrating over. So our first example, evaluate the double integral over S of x cubed z ds, where S is the cylinder parameterized by r of uv, which is components u, 9 minus v squared, and v, bound on 0 to 4 for u and 0 to 1 for v. Okay, so we already have our surface parametrically, so using that first definition will make more sense here. So we need to find the two tangent vectors and cross them. So let's go straight to the cross product, and we'll just find the tangent vectors as we set up this cross product. So ijk. So partial of r with respect to u is going to be 1, 0, 0. And partial of r with respect to v is going to be 0, negative 2v, 1. So the cross product here is going to be 0 minus 0, 1 minus 0, but the j component's negative, so negative 1. And then negative 2v minus 0 is negative 2v. So our first example, the cross product was relatively straightforward. That's always nice. Now we need to find the magnitude of that cross product. So that's going to be the square root of 0 squared plus negative 1 squared plus negative 2v squared. Extend that a little bit further. So that's going to be the square root of 1 plus 4v squared. Okay, so now we can rewrite the integral in terms of u and v. So we're going double integral. The function is x cubed z. So it's going to be u cubed v, replacing it with the parameterization. Then the ds becomes the square root of 1 plus 4v squared. And then dA, but we can just go directly to saying du dv. u is bound from 0 to 4, v is bound from 0 to 1. Again, just for emphasis here, that is the ds element that we're integrating over. Okay, so this is separable. So you could separate it, you could practice your integration. I'm going to skip that since really our focus is more on setting up. I'll integrate some of the later examples. And you would get 16 over 3 times 5 square root of 5 minus 1. Okay? But for me, it's more important the setup. Magnitude of that cross product to help us replace the surface area element we're integrating over, the ds. And then we replace the function in terms of u and v, and then we integrate. Our next example, evaluate the double integral over s of z ds, where s is the part of the plane x plus y plus z equals 2 in the first octant. So in this case, we can solve explicitly here. So we could say that z equals 2 minus x minus y, which will allow us to use that second definition. So we can say we have the double integral. We need to replace z because essentially we're using a trivial parameterization here, and we've defined z as 2 minus x minus y. So 2 minus x minus y. And then the square root of 1 plus, so we're thinking of this right here as your g of xy. So the partial with respect to x is going to be negative 1 squared, and then plus negative 1 squared for the partial with respect to y, and then that's dA. So we need to figure out the region that we're integrating over. So if we're in the first octant, well, then we can just think in the xy plane, since those are the parameters we're using, right? A trivial parameterization, x and y would be our parameters. So z would be 0, so really we're just looking at this region here. Intercepts would be 2. That would be y equals 2 minus x there. So I do think setting it up as a type 1 region would work out nicely here. So we have the double integral of 2 minus x minus y, square root of 3, dy dx, and y goes from 0 to 2 minus x, and then x goes from 0 to 2. And again, this would be a great example for you to practice your integration with. The answer at the end of all the integration will be 4 square root of 3 over 3. But for this second example, more focused on the setup, we have an explicitly defined surface, so we're able to use the second definition. We see what that looks like, draw out a region to figure out our bounds of integration, and then we'd go through the process of integrating and get 4 rad 3 over 3 for this surface integral. Now evaluate the double integral over s of z squared ds, where s is the part of the sphere, x squared plus y squared plus z squared equals 4, above the plane z equals 1. So now we have a sphere. We can define this parametrically. So let's go r of theta phi. So that's going to be 2 sine phi cos theta, 2 sine phi sine theta, and 2 cosine phi. Our bounds on theta are just going to be 0 to 2 pi. And for phi, we have to figure out what z equals 1 would define. So we can say that 1 equals 2 cosine phi. So 1/2 equals cosine phi, which says phi equals pi over 3. So our bounds on phi, 0 to pi over 3. Now, in this instance, we could also solve explicitly because we only have the part of the sphere above the plane. So we could write it as z equals the positive square root of 4 minus x squared minus y squared and use the second definition. Right? So we do have two approaches here. Now the magnitude of the cross product, we can jump all the way to that point as we discussed in the previous video on surface area. The magnitude of this cross product is going to be 4 sine phi, which is really nothing more than rho squared sine phi from our work with spherical coordinates. So that does save us a bit of time and effort here. Otherwise, we'd be finding two tangent vectors, the cross product, and we could do it. It would just take time. Okay, so now setting up double integral of z squared, so that's 2 cosine phi based on our parameterization squared. And then we're replacing ds with 4 sine phi, and we can just go d theta d phi. Theta goes 0 to 2 pi, phi goes 0 to pi over 3. And again, this is the ds element. So here we can separate, so 4 times 4, so we could pull a 16 out, and then integral from 0 to pi over 3 of cosine squared phi sine phi d phi times the integral from 0 to 2 pi of 1 d theta. So this one we will actually integrate out. So for the first integral, underline cos phi as the u in a traditional u substitution. Du then would be negative sine phi. So I'll circle that. That's your du term. So we get 16 times negative cos cubed phi over 3. Evaluate that from 0 to pi over 3. And then theta evaluated from 0 to 2 pi. So that's going to be 16 times, so cosine of pi over 3 is a half, so to the third would be 1/8, divided by 3 would be 1/24, so negative 1 over 24, and then minus a negative will be plus 1/3, cosine of 0 is 1, and then times 2 pi. So we get 32 pi times, so that would be 8 over 24, so 7 over 24, and then common factor of 8, so 28 pi over 3 would be the value of this surface integral over the sphere with the scalar function of z squared. Now evaluate the double integral over S of x squared plus y squared ds, where S is the boundary of the region enclosed by the cone z equals square root of x squared plus y squared, and the plane z equals 2. So here we have a closed surface. So if we draw it out, it's the first one we're going to draw out, we have a cone, and then we have the plane z equals 2. So here the surface that we're integrating over is the cone, and then the disk that closes the cone, which we'll call S2. So the surface S is the union of S1 and S2. So here there are two surfaces, the cone and the plane, that make up the surface we're integrating over. So this is a closed region. Now we've done this for line integrals where we just had to separately evaluate the line integral over each curve that made up the bigger curve C. So we're going to do the same thing here. We have to do separate surface integrals over the cone and then the plane, and then add up the results to get the integral we're looking for. Okay, so we'll start over S1. So that's the cone. All right, so cone is defined explicitly, so we can use that second definition. So we have the double integral over the domain D, not sure what that is yet. And then the function is x squared plus y squared. So that stays x squared plus y squared, because explicitly we're using a trivial parameterization. So x and y are the parameters, so they stay. Then the square root of 1 plus, so this is what we think of as the g function in that definition. So the partial with respect to x is going to be x over square root of x squared plus y squared squared. And then with respect to y, it's y over square root of x squared plus y squared squared dA. So we need to figure out what region we're integrating over. Well, the intersection of the plane and the cone is a circle. And it's a circle of radius 2. So in the xy plane. we are going to integrate over a circle of radius 2. So that means polar is going to make sense as far as integrating this region out. So we can convert this to polar while we're simplifying here. So it's going to be the double integral. X squared is r squared. And then you'd have x squared over x squared plus y squared over x squared plus y squared. That's going to be 1. Plus 1 is 2. So this is just going to be square root of 2. dA becomes r dr d theta because we are converting to polar. We didn't use a polar type parameterization. And then we're going 0 to 2, 0 to 2 pi. Okay, so we can integrate this out because we want the value here for our work later. So this is separable. So we get square root of 2, integral from 0 to 2 pi of 1 d theta times the integral from 0 to 2 of r cubed dr. So that's going to be square root of 2 times theta evaluated from 0 to 2 pi times 1/4 r to the 4th from 0 to 2. So we get rad 2 times 2 pi, 2 to the 4th is 16, times 1/4 is 4. So we get 8 pi square root of 2. So that's over the first part of our surface. Now we need to go over the second part of our surface. So over S2, which is the plane. Now S2, since we're on a plane, that surface is two-dimensional. So in this instance, ds is going to be equivalent to dA. We don't have to find any scale factor that makes those two equivalent because our surface is already two-dimensional. And if you wanted to, you can confirm, let's spell that right, confirm with the parameterization r of xy, so a trivial parameterization, which looks like this, x, y, 2. Right? Since we have the plane z equals 2, z is 2 in the parameterization, and then x and y are free. Those are the two parameters. If you found the cross product of the partial of this with respect to x and the partial of this with respect to y, you would find that the magnitude of that cross product is 1, which then sets us up for saying ds is equal to dA. So we're still integrating over the same region, right? So we're still integrating over that circle of radius 2. So we get double integral. Here we can just go straight to polar. So x squared plus y squared is r squared. dA is going to be r dr d theta. 0 to 2, 0 to 2 pi. Which if we evaluate out is just going to be 8 pi. It's basically the same integral we just got without the factor of square root of 2. So that means that the double integral over the closed surface S of x squared plus y squared ds, which is the original question we were looking for, is 8 pi plus 8 pi rad 2, which we could say is 8 pi times 1 plus square root of 2. Right, so this is our first example where the surface is a closed surface. And that's definitely something we're going to explore as we continue on with more surface integration. And we bring in vector fields, and we bring in some of the theorems that we're going to finish this course off with. Now, what does a surface integral of a scalar function represent? Like, why is it useful to find? Well, if the function rho of xyz represents the mass density at a point xyz on the surface S, then the mass of the surface is defined by that surface integral. So double integral over the surface S. Now our function is the mass density function integrating over surface ds. So that's where this type of integration can be useful if we're trying to find the mass of a surface. So find the mass of an object that occupies the part of the paraboloid z equals 4 minus x squared minus y squared between the planes z equals 0 and z equals 3 if its density function is rho of xyz equaling to x squared over x squared plus y squared. Right, so an object, think of a piece of foil, a thin sheet, right? That's the object, and it perfectly fits in the shape of the surface that we're defining, and we're going to find the mass of that object. Okay, so explicitly defined surface, so we can use that second definition. We have our density function, that's our scalar function. So we're going to say the mass is the double integral over the region D, scalar function x squared over x squared plus y squared, and then square root of 1 plus negative 2x squared plus negative 2y squared dA. We need to figure out what the area we're integrating over is. So if we think about the intersection of the paraboloid with the two planes, so at z equals 0, we would have x squared plus y squared equals 4. So we have a circle of radius 2. And then when z equals 3, we'd have x squared plus y squared equals 1. So we have a circle of radius 1. So the region we're integrating over is the ring shape here. So polar, again, makes a lot of sense. So we can convert this double integral to polar. So that's going to be the double integral of r squared cos squared theta over r squared, square root of, so this would be 1 plus 4x squared plus 4y squared, so 1 plus 4r squared. And then the dA, since we're converting to polar, is r dr d theta. R goes from 1 to 2. Theta goes from 0 to 2 pi. We do get a bit of simplification here. The r squared terms would cross out. So we're integrating cos squared theta times square root of 1 plus 4r squared times r dr d theta. So it is separable. So here it's been separated for us. Now we just need to proceed with the integration. So for cos squared, we need to replace it with the double angle identity. So 1/2 plus cosine 2 theta over 2 d theta. And then I'll just rewrite the other integral. Everything's set up nicely there. So with respect to theta, for the second term at least, underline 2 theta, that would be your u in the u sub. Then we need an extra factor of 2. That would be the du. So we get theta over 2 plus sine 2 theta over 4 from 0 to 2 pi. And then for r, underline 1 plus 4r squared as our u. Then du would be 8r. So we need a factor of 8 there. So this is going to be 1/8, and then 1 plus 4r squared to the 3/2 times 2/3 from 1 to 2. So now we just have to evaluate. So we get pi, and then 0, and then 0 and 0. So pi times 1/8 times 2/3 is 1/12 times, plug in 2, so that's 4 times 4 is 16, plus 1 is 17. 17 to the 3/2 is 17 square root of 17. And then minus, plug in 1, so that's 4 plus 1, that's 5. So that's 5 square root of 5. So we get pi over 12 times 17 square root of 17 minus 5 square root of 5. Okay, so that's how we evaluate the surface integral of a scalar function. We redefine the function in terms of our parameterization. Then we need to replace that ds element that we're integrating over. If it's parametrically, we replace it with the magnitude of the cross product of the partial of r with respect to u and the partial of r with respect to v. If the surface is defined explicitly, we can take a more direct approach, as we did in this example, and set up the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared. So we have a few different options here. Next task is going to be bringing in a vector field, but before we get there, let's practice with this skill, and I'll see you in the next video.